So 4.2, we have energy and conservations of energy. So how we define energy? When we do work, actually it involves a transfer of energy from one form to another form. For example, the work you done to lift a box are going to change to the potential energy at its final positions. So energy basically can be defined as the system ability to do works. So energy is a scalar quantity. The SI unit for energy is joule. Basically, in our discussion for topic 4, we are going to focus on mechanical energy. And there are two types of mechanical energy, which is potential energy, we represent by capital U. Second one is kinetic energy, we represent by capital K. So, potential energy U is actually referred to the energy that's stored in a body or a system because of its position, shape, or state. Basically, potential energy can be categorized into two, which is gravitational potential energy and elastic potential energy. So, what is gravitational potential energy? Gravitational potential energy is the energy that we store in a body or a system because of its positions. The positions here normally is referred to the height. So when we raise an object to a certain height, then the object will gain gravitational potential energy. So this is the equation we use to calculate the gravitational potential energy. We have U equal to mgh. So the m is referred to the mass of the object or the body. G is referred to the acceleration due to gravity. So if the object is on the earth, so the value of G will be 9.81. The h will refer to the height of the body from its initial positions. Okay. Then the second type of potential energy is elastic potential energy. This is the energy that's stored in an elastic materials as the result of their stretching or compressing. So the example of elastic materials that we can have in our real life is spring. Spring is the most common example whereby when we compress the spring or when we're stretching the spring, we will store elastic potential energy. So this is the equation we use to calculate elastic potential energy. U is equal to half kx squared, where k is referred to the spring constant. Different type of spring, they are going to have different value of spring constant. X is referred to the amount of compression or the extension of the spring. Or we might also calculate elastic potential energy by using equation half Fx. So F is referred to the applied force, the force that we apply to compress the spring or stretching the spring. So again, spring will be the most common device which we can store elastic potential energy due to its compression or stretching. So normally when we put an object on the spring and we compress the spring will store elastic potential energy. Upon release, the elastic potential energy will transform to the kinetic energy of the object. Okay? So we can use Hooke's law in order to relate the force that required to compress the spring with the amount of compression or extension, whereby we have F equal to negative Kx. So the Fs actually is referred to the restoring force of the spring. K is referred to the spring constant or force constant. X is the amount of stretch or compressions. So for these Hooke's law equations, you will find out that in the equation we have a negative sign. So class, this negative sign actually indicates that the direction of the restoring force in the spring is always opposite to the directions of amount of stretching or compressions. You might refer to the figure given in your lecture notes. So you will find out that the restoring force that try to pull the spring back to its equilibrium positions will be always opposite to the value of x. For example, if the if the spring is being stretching, the x is positive, the restoring force will be negative. Same goes for compressions. When we compress the spring, the x is negative, but our restoring force will be positive. So class, anyhow, for any calculations, we might ignore the negative signs and we just use F equal to kx, whereby the F will be the applied force that we use to compress the spring or stretching the spring. So if we refer to the dimension of spring constant, the dimension for K will be the dimension of F divided by the dimension of X. So the dimension for F is MLT negative 2 divided by the dimension for X is capital L. So we will get the dimension for spring constant K will be MT negative 2. So by referring to the dimensions for spring constant, we can get the SI unit for K, which is kg per second squared, or we have Newton per meter. So from the Hooke's law, without any negative sign, a restoring force against extension of the spring X can be shown in figure below. So the force that we apply to stretch or compress the spring is directly proportional. So we will get a straight line. Then we can calculate the area under the graph. So the area under the Fs graph actually represents the work done to stretch the spring. So we might have work done to stretch the spring to a distance x will be area under the Fx graph. So it will be half multiplied the F multiplied the extension x. So refer to Hooke's law, F is equal to kx. So we might have work equal to half kx squared. And this amount of work done will be stored in the spring as elastic potential energy. Then we move on to another type of mechanical energy, which is kinetic energy. We represent by capital K. So this is the energy of a body due to its motions. So motion, then you will understood that when the object in motion means the object has velocity. So this is the formula to calculate the kinetic energy. Kinetic energy will be half mv squared. So the m is referred to the mass of the body and v is referred to the speed of the body or the velocity of the bodies. Anyhow, bear in mind, kinetic energy is a scalar quantity. So the kinetic energy is only depends on the body's mass and also the speed of the bodies. It does not depend on the direction of the motion because it's a scalar quantities. So for the same mass and same speed, even though they are moved off in different directions, they are going to have same kinetic energy. But then our kinetic energy is directly proportional to mass. So when the mass is twice, then the kinetic energy will become twice. Same goes for the speed. The kinetic energy is directly proportional to the speed of the body squared. So for the same mass, if we double up the speed, then our kinetic energy will become 4 times. Why? Because 2v squared, it will become 4v squared. So our kinetic energy will become 4 times.